it's just,
Where is it?
yeah, how do we add,
Right.
just
Get the reservoir.
conceptually,
Tip of the tail.
for the picture, we add vectors tip to tail, right? Easy to do in certain situations if we're talking about motion or some kind of vectors that are all collinear, right? That's easy, piece of cake. If the vectors even are at right angles, not a big deal. But if the vectors are not, there's only one reasonable alternative here. The geometric alternative is horrible, right? We gotta invoke all this non-right triangle trigonometry and it's not very fun. But we can take advantage of the fact that all vectors can be broken into right angle components and make life easy, right? So I want to go through just 3 problems here that are just like the ones you're going to do on your problem set. So this is big. And let's kind of work towards being able to handle multiple non-orthogonal, is our fancy word for it, vectors that are not along the x and y directions. Vectors, and you see it's no big deal. So let's try this one. Okay, let's say we got a cruise ship that's cruising along at 8.01 meters per second at 53 degrees north of east relative to the water within a, oh, that's not the one I want to do, that's the hard one. Hang on.
We should do. Let's do the hard one.
Yeah, let's not do the hard one first.
The one you want to do is the spikeball video.
Is that the one I want to do?
Yeah.
Oh, okay.
You saw it on your notes up
Gotcha.
there.
Gotcha. Did you? Oh, I know what I'm doing wrong.
I saw Friday in the spikeball video in capital letters
Squirrels.
underlined.
It says physics. Oh, that's not how you spell spike ball.
No. Uh-huh. Let's see how this works. All right. Okay, so let's try going preview. This is what I want. Oh, that's much better.
It looks a little bit easier. Just
Yeah.
a much.
Yeah, that's easier.
It's not a bad cruise ship.
Okay, so let's try this guy. Okay, so first we're going to do is we're just going to practice taking a vector, but we could do this for any number of vectors, and we're going to break it into components. First things first. Okay, so we got some vector v of magnitude 3.6 at an angle of 13 degrees from the positive x-axis. We want to break this into x and y components. No big deal. Does that look a little fuzzy?
I think it looks a lot better than it used to personally.
Really?
Yeah, I do.
Seems a little less fuzzy.
Seems like something happened.
I don't know, you still haven't figured out how to spell spikeball.
Yeah.
It looks beautiful. Wait, calibrate.
This is LA.
Wait, no. Oh gosh.
No. Where'd it go?
You beat the calibration.
Yeah.
You're supposed to calibrate it. Yeah, calibrate it.
I don't think that one. Now I got to hit all these.
Yeah,
So
see,
there
you
we go.
gotta calibrate.
Oh, good. All right.
Ah, that's awesome.
Much better. All right.
Wait, where is it fuzzy?
It just seems fuzzy right here.
Oh, I can mess with up there, I guess.
Well, at the end, if we need to, we'll do that. All right. So. Okay, so let's go. So we got our vector, right? It's going to go at a 13-degree angle, so that's pretty shallow. So we'll just say it. I mean, that'd be perfect. It looks like that, right? There's our vector. Okay, so this is 13 degrees. And we're going to break that into components. Okay, what are we going to call this one?
A.
No, what are we going to call this one?
V.
V sub x. Good. Okay, good.
A sub X.
And this one is v sub y. Good. So if we call this vector v, then this guy is v sub x, and this guy is v sub y for x component and y component, right? And this is a right triangle. Okay, so we talked about a method for doing this yesterday. what's the little phrase that I gotta write down that reminds me? SOHCAHTOA, all right. So, TOA. So let's see here. What is SO? What is that telling us? Right here, what is it? Okay, sine of theta, sine of whatever my angle is the ratio of opposite divided by hypotenuse, right? So sine theta equals opposite over hypotenuse. Okay, let's see. Nathan, what's this mean? What's CA? What's the C stand for? Cosine. Good. Cosine, what's the ratio? Cosine of an angle, cosine of 13, or whatever you want to call it, equals ratio of what over what? Adjacent over hypotenuse. Very good. And TOA, what do we got for that? Michaela, what's TOA? Is equal to the ratio of opposite over adjacent. Good. Okay, so we've got it. First of all, we have to identify what are the sides. So if this is my angle, hypotenuse is easy. We start there. Where's that? Okay, right there. What's opposite?
Across from the angle.
Okay, the one that it's opposite across from it, right? It's looking at it, so that's opposite. Adjacent means next to. All right, so if we want to find v sub x, now we got to just think about which is the SOHCAHTOA relationship that's going to link v sub x to v, right? Because v is the one that we know. We actually have a magnitude for v, don't we? It's 3.6, right? So let's go ahead and just write that number down here too. So this one is 3.6 is the magnitude. Okay, so if I want to find v sub x, which one of those SOHCAHTOA relationships is going to be the one that relates these two? Ka. Good, because it's adjacent and hypotenuse, right? So we got cosine of 13 degrees equals the ratio of adjacent, which is v sub x, over hypotenuse, which is, in this case, 3.6, right? Okay, so if we got to do two algebra steps here, but when we're all done with this, I want to kind of come up with a shortcut so we can not have to go through these steps every time, right? If I want to solve for v sub x, and that doesn't look like a sub x, let's, come on. It's supposed to be v sub x. If I'm going to solve for v sub x, what do I have to do to get to v sub x by itself? Multiply both sides by 3.6, right? So this is going to give us the equation v sub x equals 3.6 times cosine 13 degrees. And that's just going to be a number, right? Okay, what am I going to do to find v sub y? Sine. I'm going to use sine that time. Take advantage of the fact that sine 13 degrees equals v sub y over 3.6. So that tells us v sub y equals 3.6 times sine 13 degrees. Now, is there a way here that we could just skip right to that step? I mean, we always can just start from the trig relationship. You've always got that to fall back on, right? We can just define the SOHCAHTOA relationship and solve for the unknown. But think about this now in terms of what sine and cosine functions look like. Okay? And if you're not real familiar with them, some of you are, you can help us out a little bit here. So what are the values of sine and cosine constrained? They're constrained to be in what range of values? Okay, but the outputs. Yeah, we can say it again. Okay, now those are inputs, right? We input angles into trig functions, and the trig functions spit out numbers. Like we would take the cosine of an angle or the sine of an angle, and they're going to spit out numbers, okay, that our calculator will tell us. The outputs, though, so what is the range of outputs of a sine or a cosine function? Well, -1 to 1, right? Okay. So, but the point is, their absolute value of the output is going to be less than or equal to 1, right? If we look at it, let me just really quickly, we'll just graph what one looks like. Not that this is important for us, but if we want to just look at what like a sine function looks like, it just looks like that, right? and that's 1, and that's -1. Cosine function looks exactly the same, only it just starts in a slightly different place, right? But no matter what you do, you can't get outputs bigger than 1. So the point of that is, if I multiply a number by a sine or a cosine, what can you definitely tell me about the product?
It's gonna be positive, negative.
Okay, it could be positive or negative,
It's
but
gonna be less than the hypotenuse.
okay, so it's gonna be, the output, if I multiply by a trig function, the result is always gonna be, at best, equal to the number, and that's rare, right? That's only at a few special places on the unit circle or a few values of angles. But the vast majority of the time, the output is gonna be less than. It could never be greater than, right? So if I multiply by a trig function, I'm making something smaller, right? Now, what are we trying to do here? If we're relating v sub x to the hypotenuse, which is always the longest side in the triangle? The hypotenuse, right? So if I want to find the length of one of these other sides of the right triangle, v sub x or v sub y, right? Multiplying by a trig function is going to do the trick if I'm multiplying by the biggest side. Does that make sense? So we always know that if we're trying to find a component of a vector, we're going to multiply by either sine or cosine to figure out which one it is. That's where you just think SOHCAHTOA, right? I know if I want to find, for example, v sub x, I'm going to multiply the hypotenuse by something. Which trig function? Well, cosine, because that's the one that links adjacent and hypotenuse. See what I'm saying? It's just a little shortcut, but we're going to be doing this enough that actually it's kind of helpful to just get to skip that step each time, right? Okay, so then we could determine what these components are if we put them in a calculator, and we're just going to get some numbers back. We talked about that yesterday. No big deal. But these are the exact answers, right? Any decimal on a calculator is going to be an approximation of these, but these are exact. Okay, how about this guy? Oh, wrong one. We got one more to do. Okay, we're building up to this one. Okay, so how about this one? Powerboat, yep. Okay, so a powerboat heads due east at 9.3 meters per second, cut that off a little bit, relative to the water, across a river that flows due north at 4.5 meters per second. So seen from let's say the shore or a hovering helicopter that's stationary, what's that boat going to do? It's going to go at an angle, isn't it? Because it's going relative to the water due east, but then the water's carrying it north at the same time, right? So if I wanted to find the resultant velocity of this, the actual velocity relative to the shore or to, like a stationary bridge above the river, something like that, I've got to add up those velocities. They're vectors, so I got to add them up as vectors, right? Okay. So let's represent this. So we've got, once again, there's our north and east directions, let's say. So here's the velocity of which one's going due east? The boat. Okay, so here's the velocity of the boat relative to the water, right? And that is 9.3. And this is the velocity of the water relative to the shore. Okay, so something like that, right? And if I add those up tip to tail, the velocity of the boat relative to the water plus the velocity of the water relative to the shore, there's something kind of interesting that happens here. Look what shows kind of bad subscripts here, unfortunately, but I'll see. So we got V sub VW, velocity of the boat relative to the water, plus the velocity of the water relative to the shore, ends up giving us, how would you describe it? The velocity of the boat relative to shore. That's not a commentary on the value of this problem. This is a good problem, I'm sure. Right, so we're gonna add those up tip to tail. And what was this? This was 4.5?
I see what you did there, it's because it's purple.
Exactly.
Yeah,
Purple is
you got it.
nice.
That works.
You got it. There you go. You're right on top of it as usual. It's come to expect that from you. That's good. Okay, so then we want to come up with the magnitude of the velocity and the direction. Now the magnitude we can do. How are we going to find the magnitude?
Squares.
Okay, so Pythagorean theorem, blue squared plus red squared equals purple squared. So purple equals the square root of blue squared plus red squared, right? No big deal. We can figure that out. Somebody tell me what that is real quick.
Didn't know, get on my calculator just for this.
Square root of 9.3 squared plus 4.5 squared is roughly equal, rounded to, let's say 2 places. What do we get? 10.33 meters per second. Okay? Makes sense? Okay. So what about the direction though? That's easy, right? But the direction is we don't know how to do that.
Oh, let me not do it.
Okay, the direction. So if we want to find, really what we're trying to find is that angle theta, right? Okay, here's what we can do though. We can go back to those same trig relationships that we had for SOHCAHTOA, and we can use those to solve for theta. Okay, it's a different operation or a different function than you're used to, but same concept as always. So we've got, for example, we knew that sine theta equals ratio of red over purple, right? So that was, we'll just do it this way. I'm gonna write it this way. V sub WS divided by V sub VS, and then cosine theta equals the ratio of adjacent over hypotenuse. What's that? VW over V sub VS, and then we've got tangent, right? And that's opposite over adjacent. I'm going to write that one using, we're going to use that one. I want you to tell me why though here in a second. 4.5 over 9.3.
Because 10.33 is
Exactly. Okay, good. So we're going to use one of these relationships and solve for theta, but we want to use the one that's not incorporating any rounded numbers, right? So if we had left this on our calculator, it would have been fine, right? But we didn't. I wrote down a rounded number. We don't want to accumulate rounding error, so propagate error, and so we're not going to use that one. We'll use the two exact measurements, or the two measurements that were given to us, right? Okay, but what do we do with this? How are we going to solve that?
Inverse versus just the inverse.
Okay, good. So we've got to isolate the variable, but to isolate the variable, somehow that would mean we have to unlock it from the tangent function, right? And so we're going to take the inverse of a tangent function. Think what it does, what the inverse of a relation does. If I take, this goes back to like probably algebra 2, I'm guessing. So if f of x is the function, then its inverse we would write as f inverse, right? So we know that f inverse of x is equal to what? X. Okay. And we also know that f inverse of f of x must equal that. They have to undo each other. Okay, what's the inverse function of tangent? Well, it's inverse tangent, or arctangent we sometimes call that. Okay, so really all you got to know here in terms of pragmatic approach to solving these problems is, on your calculator, you're going to use the arc, I can't remember the inverse or arc, I don't remember what they call it, one of the two. We're going to use that feature, right?
It just says tangent 1.
Okay, so that's a way of writing inverse tangent, okay? So then we just end up getting if I take the arc tangent of both sides, or the inverse tangent, just two different names for the same thing, the inverse tangent and the tangent cancel, and I end up getting theta equals inverse tangent of that ratio, 4.5 over 9.3, okay? So let's go pull up the calculator, show you how you do this. Okay, so inverse tangent sits behind the tangent. Okay, inverse tangent of 4.5 divided by 9.3 equals. Okay, that just seems kind of weird. What did I mean, that doesn't seem like, that can't be right, can it? Ah, exactly, it's in radians, isn't it? It's in radians. Okay, so I've got it, because we can tell that's not right. I'm going over roughly 9, I'm going up 4.5. That's clearly an angle that's bigger than 1 degree, right? Okay, so what can I do then to fix that? Okay, one thing I could always do is I could just go to mode, flip to degrees, and let's just repeat the same calculation. Okay. So now I can just go up and grab the same calculation again, hit enter, and there it tells me, okay? I'm wondering if I could also just put degrees at the end of that. Should we try it? Let's just see. Why is that thing doing that? What do you think? River, what's going on?
What's going on? Well, it just kept going higher and higher and higher.
Yeah, something's...
Actually, that's happened before, yeah.
It has happened before today?
Not today.
Oh.
No, not this one. But like, there's been times, I can't remember what class it was. I was in one class where it just started like keep on going faster and faster, and then it just poof.
Really?
Yeah.
Oh, no, like,
Yeah.
I feel like I was in that class.
Yeah.
Huh.
It was like very
What, the other day we were watching film for football and we started to look at it, right when we look up there, it's just no light bulb below us. You'll someday.
Okay, let's just try. I just want to see if this will work. We're just messing around here. So if I take one of these,
I don't know if you could, because those aren't actually degrees.
yeah, but I'm wondering if I put the whole thing in. Let's try putting a degree there, just see what happens. Because the output of arc tangent should be degrees.
I already tried all the R to whatever, R to PR and R to B theta. So,
Didn't do it.
yeah, well, I don't know if it does it.
So if I go second angle, degrees, yeah, I don't think that's going to work. No, oh,
You
No.
could always just,
No,
if
well
it's in
said.
radians, times it by 180.
yeah, you could, exactly. The other thing you could do is you could multiply by the changer, which is 180 over pi.
Who wants to do that?
I'm wondering, you could also maybe do, oh, I gotta get the degrees out of there, don't I? Whoops. Okay, so there's the answer in radians. I think I could then maybe do a conversion. What if we did this? What if we went second? Just want to give you all your options here. Oh, there we go. Radians
Are you careful?
to,
Oh, unless I put it on the wrong side.
Is that 6 maybe?
What I tried is both of the R to whatever, just, and then in the parentheses, I put the .44. I put the .44 to enter the number in there now. But I already tried both of those, and it just gives you an error if you just put a number in there, so possibly.
No, it's second, the negative sign, or, yeah, second, and then the negative sign is where the answer is.
oh, yeah, to get your, gotcha. Okay, let's see, I'm about ready to stop messing around with this, but I'm just real curious if we can make this work here. So math,
I don't think.
numbers,
I bet you just really
fraction,
like-
decimal. No, I don't think I don't think there's an easy way to do it. I think you just want to either multiply by the changer or just put it in degrees mode. Okay. Either way, doesn't matter. I give up. Okay, so we got, let's put it in degrees. So we get an answer of, whoops. About rounded to how many places can we keep? I think we can only keep 2, can't we?
Yeah.
Right. So it'd be 26 degrees. Okay. So that gives us, so now we have the absolute direction there, right? Make sense? Okay. All right, so we're ready to move on to the big guns here.
Well, it is a boat, so shouldn't we have it in DMS or whatever?
No, we'll just go that way.
It's a boat, no.
So how about this guy? This looks complicated. A ship cruises at 8.01 meters per second at 53 degrees north of east relative to the water within a current that flows due northeast at 6.78 meters per second. A passenger rides a scooter along the deck at 3.74 meters per second at 54.0 degrees east of north relative to the deck of the boat. So we got 3 things happening at once, right? The boat is traveling along the water. The boat is traveling along the water. The current is moving it in a certain direction as it moves along the water. And then the guy's riding his scooter in some other direction.
Should you say north up east?
So north of east, what does that mean? If I don't give you any degree measure, but I say north of east, what am I implying? Northeast, yeah, 45 degrees, right?
I can't do this in.
You could.
So, but.
Actually, it says that flows due northeast.
But when it's 43 degrees.
Oh, I got you. North of east. Okay, so that means you're starting east, and you're gonna pivot north of east that far. Make sense? Okay.
So, just 53 degrees.
Yeah.
Yeah.
Yeah. Right. Okay, but I'm gonna give you some problems where maybe it'll say something like 53 degrees south of west, and so then you got to start west and move south of west. Right?
Why don't we just use 360 degrees like compass?
You can't. There's some tricks associated with that. I don't want to get. I'm not going to go there today. So on this first assignment, I'm gonna relegate this just to things that are north of east. But then we'll expand that to other directions next. There's some tricks you can do that make that easier to deal with. But I just don't want to overload you all at once. So let's do this one then. How are we going to deal with adding up these 3 vectors?
So start with the first one.
Okay, take the first one. Ship cruises at 8.01 meters per second, 53 degrees north of east. So we're going to take the first vector and break it into components, right? Okay, so the first one looks like this. So this guy is, we'll make this one blue. So that one's 50, it doesn't have to be exact, we're just representing this, but it's going to be 8.01 is the magnitude, 53.0 degrees, right? Okay, so let's find those components. So if I want to find the x component, so what are we calling this? This was the ship. Okay, so we'll call it S for ship, S sub x and S sub y, how about? What's the equation? Let's jump right to it if we can. What's going to be the equation for S sub x? S sub x equals 8.01, right? We're going to start with the length of the vector and then just multiply it by the correct trig function to get the component. So which trig function in this case is going to relate this angle and those two? Cosine of 53.0. Okay, good. All right, so S sub y equals what? 8.01 sine 53.0, right? Degrees. Okay. Let's make a table on the other page. So we know that that's going to be a horizontal component and that's a vertical component, right? Okay. We can go to the next page. And we're going to do some columns. We got the vector column, we got the x component column, and we got the y component column. So the first one was S, and we got, let me write this down, 8.01. Okay, 8.01 cosine 53.0, 8.01 sine 53.0. Okay, next one. Current. Okay, so the current is flowing due northeast. So what's that angle? 45. Okay, so now we've got C sub x, C sub y, and the current is 6.78 standard meters per second. Right. So same as before, C sub x is going to equal 6.78 cosine 45, right? How many sig figs is that to? There's really no limit, is there? I mean, we're told that it's due northeast, so when we're looking to find the limiting number of sig figs, it's not going to come from that, is it? Right? Okay. So I'll just call it 45. But we know we're not going to count those sig figs. That make sense? Okay. C sub y 6.78 sine 45. Remember those 6.78. Remember that 6.78. 6.78. 6.78. Okay, and then last one we had was the passenger on the scooter. So we'll call it P for passenger. How about? So the passenger is going 54 degrees east of north. Ooh, tricky. 54 degrees east of north. So if I draw this then, that one's going to be green. That means that this is the angle, doesn't it? Right? Okay. 54.0. So we got a couple options here. One of them is, okay, so that is 3.74. But using that angle, we would have to use those vectors to be the components, right?
Does it matter which way it goes?
What do you mean? We could. Then what angle would I have to use? 36, right? Everybody see that? Because these add up to 90, so I could. You're right, I could have also made that 36 and used the bottom triangle. Either way is going to give me the same answer. I want to use this one just to illustrate a point though. So this is C sub y, no not C, P, right? P sub y and P sub x. Okay, so what is P sub x equal to this time? Now be careful. Sine, isn't it? Because P sub x is opposite the angle, the way we've got it drawn, okay? And P sub y equals 3.74, then cosine 54.0. Okay, so let's transfer those to the other page.
Yeah, absolutely.
Okay, and that was P. Okay, what are we gonna do? Add them up to get the resultant. So let's call the resultant R. And this is just calculator work, right? So let's, this seems pretty innocuous here, but let's look at this, and I want to show you how you definitely want to do this in order to not lose any precision because of rounding. Okay, so we'll go to the calculator. And we want to be in degrees mode, which I already did, didn't I? Oh, are you kidding me?
No.
Oh.
You could just write us know something.
Yeah.
I guess you should.
Man.
I'm pretty sure I got the answer.